Kia ora koutou, and welcome to the final Medical Forum Hot Topic for 2017. So once per quarter, we've been running these hot topics on particular medical areas of interest, and today's topic is on antimicrobial resistance, which I'm sure you'll agree is an incredibly important challenge coming up for us over the next few years. And so I'm delighted to introduce today Dr. James Osher and Kyle Hards from the Department of Micro and Immunology, and James, you're from Micro as well, and Southern Community Labs. So thank you very much for coming and speaking us today. So we're going to have James talking first, followed by Kyle, about their view on the upcoming antimicrobial resistance challenge. Thank you very much.
Thanks, Julia. So it's a talk of two halves. I'm going to start off telling you what the problem is, and then Kyle's going to tell you what the solution is, or at least part of the solution. So let's see if this thing works. So I'm sure that it takes no convincing everyone in this room that antibiotics really have transformed modern medicine. So here's an example of a couple of papers separated by over almost 70 years. The first one published really at the dawn of the antibiotic era, looking at the rates of the clinical outcome of patients with Staph aureus bacteremia, and then a similar paper from Australia and New Zealand from 2009. And what you can see is the mortality rate was extremely high prior to the antibiotic era, and that it has dropped while it's still high in the antibiotic era, has dropped markedly. And also, what I haven't shown here is also the people who are getting Staph aureus bacteremia has really changed. It used to be people who were young and healthy in their teens and 20s who were getting Staph aureus bacteremia. Now it's people in their old age. Unfortunately, we're seeing the rise of antimicrobial resistance, a 21st century nightmare. So here, this is New Zealand data from ESR, looking at the rates of MRSA, which have been climbing. Currently in Dunedin, Otago, we're running at around 9% of our Staph aureus MRSA. And we know that if you get a bacteremia with MRSA, your mortality rate is doubled compared to if you have it with methicillin-susceptible Staph aureus bacteremia. Of perhaps more concern is the emergence of multi-drug-resistant gram-negatives, such as Enterobacteriaceae, which is the family that includes E. coli, Klebsiella pneumoniae, that produce extended-spectrum beta-lactamases, or ESBLs, which I'm sure many of you are familiar with, and we've really seen an exponential increase in the rates of these over the last decade, and continues to climb exponentially in the southern region. And we know that if you get a bacteremia with this, you've almost got a doubled rate risk of mortality than if you have a bacteremia with a susceptible strain of Enterobacteriaceae. So currently in Otago, Southland, we're running at approximately 2% rate of our E. coli are resistant to extended spectrum beta-lactams, but in other parts of the world the rates are much higher. So here's some data from, you can get off this excellent website where you can make these maps looking at rates of resistance in different parts of the world. We can see that in India, this has got some sort of lag on it, but in India the rates of resistance, ESBLs and E. coli are well over in excess of 80%, including in other parts of Southeast Asia where we have data for. So we're in a relatively privileged situation at the moment, but we're surrounded by a sea of resistance. It's not only resistance to extended spectrum beta-lactams that's of concern. Probably what's of greatest concern is resistance to carbapenems, our golden bullet antibiotic that we can, up until recently, have been able to use to treat pretty much anything. But if we look at the rates of resistance in Klebsiella pneumoniae in the Indian subcontinent, the rates of resistance to carbapenems are exceeding 60% of Klebsiella pneumoniae isolates producing a carbapenem A. And infections with these have an extremely high mortality rate associated. So 50% of people have died from infections with these within about a month. And your risk of dying is over threefold higher if you get an infection with a Carbapenem A producing Klebsiella pneumoniae than if you get one with a susceptible strain. To date, we haven't seen much of this in New Zealand. We've only seen 2 cases in Otago and Southland, and both have been, one was a urinary tract infection, the other was carriage that we picked up. But we're increasingly seeing these. So you can see the start of the epidemic curve taking off as it has for ESBLs as well. And to date, this year, there's been 35 isolates to the end of September that have been isolated across the country. And concerningly, not all of these are associated with overseas travel. Some patients, there's been no clear association with travel, suggesting that there may be some unknown transmission in the community. So we've done some work with John Crump and Tinon Mayat from Yangon. On's doing a PhD at the moment with John Crump, looking at rates of gram-negative resistance in Myanmar. So this is a retrospective study that we recently published. We looked at all the gram-negative isolates from blood culture isolates from 3 hospitals over a 6-month period, including the large teaching hospital, Yangon General. I think the first thing you notice is that they're not necessarily culturing as much as you might get here. We've had more gram-negative isolates than that in a much smaller hospital. But if we look at those, the usual range of suspects, E. coli, Klebsiella pneumoniae, also a bit of Salmonella, typhi and paratyphi, which we don't really see very often here, but very high rates of ESBL production. So 38% of the isolates were ESBL producers, half the E. coli, almost half the Klebsiella pneumoniae, and a high rate of Carbapenem A producers as well. And concerningly, if you just look at the isolates from the public hospital, from Yangon General, 73% of the E. coli and 100% of the Klebsiella pneumoniae either produced an ESBL or a Carbapenem A. And it was, if you don't have a empiric treatment regimen that includes Colistin, it's not possible to cover more than 80% of the isolate of the gram-negative isolates. So this is already a reality for practice of medicine in some parts of the world. So what's the big issue with these? These are multi-drug resistant. They're approaching pan-drug resistant. So this is from the original paper, the antibiogram from the original paper describing the New Delhi metallo-beta-lactamase. It was published in the Lancet Infectious Diseases back in 2010. And these isolates, as you can see, I've highlighted in red down the bottom, the only 2 antibiotics that really remain effective. Tigecycline was effective in 2/3, and Colistin was effective in almost all of them, barring a few intrinsically resistant isolates. But these are toxic antibiotics. Tigecycline has got a warning with it, in that the mortality rate is higher in those who receive it than those who don't. And Colistin is an old drug, but a very toxic drug, and one which we've avoided for many years. Unfortunately, the mobile or plasma-mediated Colistin resistance was recently described. This gene MCR1 was described in the Lancet Infectious Diseases last year by a group in China, and they looked at. They found this in animals at high rates in pigs, with almost 25% or roughly 20% of the isolates of pigs at slaughter contained this gene. They had isolates that contain this gene. They could also detect it in food, meat in the supermarkets, and then they could also detect it in a small number of patients as well, suggesting that the genie was already out of the bottle for resistance to Colistin. And part of the reason is that Colistin's been widely used in agricultural practice and has been used as a growth promoter in pigs in China, despite this being a last-line antibiotic. Since then, MCR1, the mobile Colistin gene, has been reported from multiple countries around the world, both in humans and in animals, suggesting that it's already widely disseminated and isn't a problem that's limited to China. And then concerningly, it has also been reported in conjunction with Carbapenem A's production, leading to truly pan-resistant infections. from not only China but also other countries around the world as well. So a report recently from the United States as well. So this has led to headlines in the popular media. So this one was from the weekend. At the top, antibiotic apocalypse. Doctors sound alarm over drug resistance, and this was around the co-reporting of resistance to colistin with Carbapenem A's production. So these headlines sort of are periodically appearing in the news. 2014, the WHO put out a report trying to sort of sum up where antimicrobial resistance is at. And to quote them, they say the problem's so serious that it threatens the achievements of modern medicine. A post-antibiotic era in which common infections and minor injuries can kill is a very real possibility for the 21st century. And I certainly think that this could have a huge impact on our practice of medicine if you consider patients who are immunosuppressed for transplants, for cancer chemotherapy, having surgery, having elective procedures with hip joints, etc. being put in. If you get an infection with one of these organisms, it's an absolute disaster. Recently, the UK government commissioned a report to try and, led by economist Jim O'Neill, who was, I think, with Goldman Sachs, looking at what the cost of antimicrobial resistance will be to the global economy. While at the moment antimicrobial resistance is predicted to account for about 700,000 deaths, they predict that by 2050, the way we're tracking at the moment globally, it's going to account for about 10 million deaths. Will exceed cancer as a cause of mortality, and there will be an uneven burden, with a greater burden in less developed countries versus those that are developed. There's also going to have a massive impact on the global economy, and they estimated that there'll be $100 trillion cumulative US dollars GDP loss due to antimicrobial resistance. So how have we got here? What can we do about it? So we can take this this is from the CDC, the Public Health Lab in the US, and simplistic view of antimicrobial resistance, but it sums it up rather nicely. So we can have organisms that become resistant. See if I can't work this thing. Become resistant maybe by mutation to an antibiotic. Then you give someone an antibiotic and you select out that organism, and it's able to take over and proliferate. But importantly, it's able to pass its genes on to another organism. And horizontal gene transfer is actually far more important than mutation for the spread of resistance. Many of the genes that are related to resistance are they're not even a single gene. They may be an operon requiring several genes, and it's not possible to derive that by mutation alone. But these genes are passed from one bacteria to another. Then we provide selective pressure, and it's able to spread around. In fact, there have been studies recently that have done metagenomic sequencing of material from the Permafrost, so 100,000 years before we ever started using antibiotics. And many of the antibiotic resistance genes that we're worried about today were present already in the Permafrost, because most of the antibiotics that we're using are made by microorganisms, and we've just purloined them, as it were, for our own use, but the resistance mechanisms already exist. And all it takes is for those genes to transfer into clinically relevant species for significant resistance. So mobile genetic elements are sort of central to this. There's a number of different players, but plasmids, transposons, integrons all make up a sort of complicated hierarchy. So we can have these resistance genes that get captured by integrons and integrated into these gene cassettes of resistance genes. These can then be sitting on mobile genetic elements such as transposons and plasmids that are able to move between different bacteria. And then we also have resistant strains of bacteria as well that seem to have a better predilection for infection than some other strains. So these mobile genetic elements, they accumulate resistance genes leading to multi-drug resistance. They also accumulate resistance genes for heavy metals and for disinfectants as well. So when we're using one class of antibiotic, we're providing a selection pressure to maintain other resistance genes as well. And even when perhaps when we're using disinfectants such as triclosan, we may be providing a selection pressure to maintain antimicrobial resistance genes in the population as well. These genes don't just sit in one bacteria, they move between bacteria, and we can think of this on a whole ecosystem level as well. So we can have transmission between human beings and hospitals and at home and in the community. Many of these resistant gram-negatives are living in the gut, most of them living in the gut, and they pass out in the feces, where we can, if we haven't got adequate sewage system, we can contaminate the environment and contaminate surface groundwater. And in fact, there's a paper that just came out a few weeks ago that looked at rivers flowing through a river flowing through the Indian city of Pune. And they could find all these Carbapenem A genes and also the MCR1 gene were present in the sludge that was in that was the sediment that was collected from the river. So these things are in the environment. From the environment, they can get. There's papers that show that wild birds shorebirds can transmit clinically relevant genes, can get into crops and soil, into livestock, and flow back into human beings as well. So we need to think of this on an ecological level, not just on a hospital or a healthcare based level. And we are increasingly close, many parts of the world, very close to our environment. There's a lot of antibiotic usage in the agricultural sector. So in the US, there's almost 4 times more antibiotic used in farming than there is in human medicine. And while we're pretty good in New Zealand, we're 3rd best in this list of countries, I think all from the OECD. And I've arrowed us at the top and then USA down the bottom. So we are much better than the US. And I think we should applaud our veterinary colleagues because they put out a statement, I think last year, where they said that their aspirational goal was that by 2030, that New Zealand Inc. will not need antibiotics for the maintenance of animal health and wellness. So they're trying to reduce their antibiotic use to reduce that selection pressure. Unfortunately, as a medical profession, we are not as good. In fact, New Zealand's got pretty high rates of antibiotic resistance, and if we look at some of the countries that we're surrounded by, it doesn't make necessarily pretty reading. We might think we're good, but we're using more than Spain or France, countries that we often think of as using large amounts of antibiotics. And if I've arrowed there at the bottom, Netherlands and France at the top. And there is a clear association between the amount of antibiotic that's used and the rates of resistance. So I've France arrowed up at the top and Netherlands down at the bottom again, just to give us a think where New Zealand might sit in. So there's Spain, so we're probably sitting somewhere up here. This is looking at the amount of outpatient use of penicillins versus the rates of penicillin non-susceptibility and Streptococcus pneumoniae, and a clear correlation. What we really need is new antibiotics, but the drug pipeline is running dry. It's looking at new FDA approvals over 5-year intervals, although the last was not quite 5 years, but we can see a decline in the investment in antibiotics development of new antibiotics by drug companies. And there's a huge cost barrier to bringing a new antibiotic to market. It's estimated it costs over $1 billion and would take well over 10 years to get a new antibiotic into the clinic. So we really need to change our model of funding drug development. WHO recently put out a global priority list for antibiotic-resistant bacteria to provide some guidance to industry as to where antibiotics need to be developed or what we need them for. And unsurprisingly, at the top was carbapenem-resistant organisms, particularly Enterobacteriaceae, the extended spectrum beta-lactamases as well. Should note that TB was not included in this list, as that's already recognised as a massive priority for antibiotic development. And in fact, of those deaths that we currently have from antimicrobial resistance, over a quarter can be attributed to resistance and tuberculosis. So what is TB? Just a quick refresher. So it's a chronic infection of the lungs, causing a granulomatous disease in the lungs. TB infects macrophages, is contained in, so you inhale TB, it infects the macrophages, is able to survive in the macrophages. You get formation of granuloma, which contain it in most cases. But when you become immunosuppressed, these can start to break down and can develop active TB and become infectious, coughing up infectious bacilli, infecting other people. And it's estimated that 2 billion people are latently infected with Mycobacterium tuberculosis worldwide. So a chest x-ray of someone with TB, so the classic right upper lobe consolidation, and some massive fast bacilli in the sputum. So there's still a major issue. So 2 billion people thought to be latently infected, potentially able to reactivate. Over 10 million new cases in 2015. This is the most recent figures from the WHO, and estimated to be 1.4 million deaths in 2015. You can see that there's an overrepresentation in sub-Saharan Africa, and there's a sort of a co-epidemic with HIV infection. Because TB is very slow growing, so for example, E. coli replicates every 30 minutes. TB takes about almost a day to replicate, and it lies dormant in macrophages for many years. Horizontal gene transfer is not such an issue in TB. Mutation tends to develop through mutation. But because it's the slow-growing nature, and for some drugs, the limited number of mutations that are required for driving resistance is an issue. And if we use a single drug, we will select out a resistant population. So you need to use at least 2 effective drugs. Because it takes such a long time to grow in the lab, we start off with 4 drugs to make sure that at least 2 are effective, and then once we have susceptibility results, we can drop back to 2 drugs. Still need to treat for a long time, at least 6 to 9 months, to get rid of the very slow-growing Mycobacterium tuberculosis. There are a number of barriers to treatment to TB that are driving drug resistance. So the long treatment duration, so you imagine you've got to take pills every day for 6 to 9 months, and you've got to have high adherence. So if you aren't taking the drugs, then there's the risk of developing drug resistance. People get lost to follow-up. The regimen's complex, they are toxic, they interact with the HIV medications, which is a big issue in sub-Saharan Africa, and increasingly we're seeing primary infection with drug-resistant TB. So multi-drug-resistant TB can be defined as TB that's resistant to at least isoniazid and rifampicin, which are 2 of the most effective frontline drugs. It was estimated in 2015 there are almost 500,000 cases of multi-drug-resistant TB diagnosed, and almost 250,000 deaths resulting from it. And you can see where the burden of multi-drug-resistant TB is, and much of it is in fact in the Indian subcontinent, but also in Russia. Of even greater concern, we've seen the emergence of extensively drug-resistant TB, or XDRTB. So this is TB that's not only resistant to isoniazid and rifampicin, but also to our second-line drugs such as any fluoroquinolone, at least one of the 3 injectable second-line agents that we've got. And these have been reported around the world, including in Dunedin, where we had New Zealand's first XDR case, and it's estimated to be almost 10% of XDR. Treatment of MDR and XDR-TB is complicated, requires combinations of second and third-line drugs, which are expensive, more toxic, less effective. We need to treat for longer, so up to 2 years or even longer. And the treatment success rates are greatly reduced. So if you look at susceptible TB patients on a global basis, 83% of people successfully complete treatment. With MDR, it's 52%, and here's the data for MDR here from the TB recent report. And I guess of concern is the large number of people who are lost to follow-up, or who failed, as these are drivers for development of XDR-TB. And the success rate with XDR-TB is even lower at 28%. So this is of a massive global concern. And the concern would be that we're going to end up back here in the sanatorium. So with that gloomy message, I'll pass over to Dr. Carl Hards, who's going to talk to you about some possible solutions.
Can everyone hear me? At the back, not blowing out anyone's ears? Great. Let's switch these slides over. Awesome. So if James has convinced you to start planning for an apocalypse, hopefully my talk can talk you out of that. So what I'm going to be talking about is some work that we're doing on conceptually developing new antibiotic themselves, as well as treatment strategies. And so what I'm going to talk about is focused on TB, mainly this idea of starving TB as a really new effective drug strategy. So I'll go into what that means. So James has covered a lot about antimicrobial resistance. What I'd also like to highlight is this concept of antimicrobial persistence. That is when a bacterium, when challenged with a drug, will form a subpopulation of cells that are resistant to antibiotics, but not because of a genetic change in their genome, not acquiring any horizontal elements. They simply are physiologically resistant to antimicrobials. We consider both resistance and persistence one major challenge combined that we need to deal with if we're going to deal with problems like MDR-TB, as well as other organisms like Staphylococcus and Salmonella as well. So what we'd really like to do is transform the treatment strategies for TB. So in this picture here, you can see this is 1 day of treatment with TB. That is injections, many drugs, toxic, not very pleasant, and additionally can involve extra IV infusions as well. And that can last from an order of 6 to 30 months. That is extremely hard to deal with. It's not tenable for treatment, and that leads to lots of cases of non-compliance, which obviously gives us more resistance, feeds back, creates a cycle. So our goal is to try and get from where we are now with these extremely long 6 to 30 month regimens and get to really short and effective therapeutics, preferably in the order of 2 weeks. We're already starting to make a few steps with some recently developed drugs. What we're going to focus on is this drug, Bataclan. So what do we need? We need drugs that are fast, but we also need to understand how they work. Otherwise, we'll never be able to innovate on them. So Bataclan is the first drug to have been licensed in 40 years. There was a 40-year innovation gap where we had no new treatments for TB. We was using the same old drugs, getting more and more resistance, and that's how we ended up here today. But Bataclan is very revolutionary. And the reason for that is it doesn't target a traditional target space. It's not cell wall biosynthesis. It's not ribosome targeting. It's not folic acid. It's targeting respiration and central metabolism. By that, I mean the process by which bacteria take, say, some sort of food or energy source. They metabolize it to make biomass and produce ATP, an essential energy source, whilst consuming oxygen. This is that classic equation that you might have learned back in high school, where you have that glucose going into CO2 and O2. It's that process. And what we're focusing on here is this process of respiration, the actual means by which we make that essential ATP. It's obviously a lot more complicated in this diagram. There are lots of proteins that sit in the membranes of bacteria, which are involved in transducing the energy in food into far more easier to utilize proton gradients, by which we can efficiently synthesize ATP. And so what Bataclan does is it specifically inhibits the ATP synthase in tuberculosis. Bearing in mind that humans obviously have very similar metabolism in the mitochondria, we have ATP synthases as well. Doesn't target that, targets TB. So it's only been FDA approved for about 5 years now on compassionate consideration for treating TB, but I've already learned quite a few things which I'd like you to take home, mainly 2 messages today. That is, through Bataclan we learned this respiration is a new and potent target space. We're calling it the 6th target space. What Bataclan has also taught us is that activating respiration, or indeed activating enzymes generally, is just as effective as developing inhibitors to enzymes. Now, both of these concepts aren't exactly new concepts. If you work in cancer, you already know this, but us bacteria people, we're a bit slow. That's why we work on more simplistic model systems. But hey, we're getting there, and we're starting to get some really good stuff out of this. So, respiration. So here's some of the original data on Bataclan. So you can see on the left here, this is simply a graph to show the specific inhibition of ATP synthesis activity with Bataclan is quite effective, low nanomolar amounts. You don't need much to inhibit the ATP synthase. By creating a genetic mutation, you can eliminate that activity. So far, that specific mutation hasn't been seen clinically, although things such as efflux pumps do come up, so obviously we want to innovate on this. But what I'd really like to point out is this kill curve here, the colony forming units per mil over time. You can see in the blue and the green here, if you take the Bataclan up to micromolar amounts, which is the amounts you put into a TB patient during therapy, it gets up to about 5 micromolar in the plasma, you can sterilize free-growing TB cultures in an order of a few weeks, so to the limit of detection here, which is obviously much better than other drugs, say isoniazid, a currently used first-line drug. We see in the purple, it goes down, persistence kicks in, not genetic resistance, persistence, and then it comes back, and then we have a big problem for treatment. So what we wanted to know is, can we target other sites in respiration? The ATP synthase is only one part of a very long process. I'm only going to talk about one aspect today, although we've investigated several, and that's oxygen consumption. So we all know oxygen consumption is quite important. I think we can all appreciate we quite like oxygen ourselves, and many organisms do. TB, for example, dedicates 2 enzymes to consuming oxygen, which is important in generating those gradients for ATP. It's upstream of ATP synthesis. So there's 2 enzymes. One's called a cytochrome BC1AA3, and the other is called a cytochrome BD. And there was this drug that was discovered called Q203 for phenotypic screening. And what we were able to show is that it targets this one of these oxygen-consuming enzymes. That was simply demonstrated by deleting the other potential enzyme for consuming oxygen and showing a nice inhibition here with reasonably low IC50s. But a real key result that I want to highlight, and this work was done in TB as well as in clinical isolates of TB, is if you compare it to Bataclan, Q203 makes Bataclan look like a bad drug. So you can see this shift of IC50 here with Q203 compared to BDQ. It's just miles away, orders of magnitude less drug required to inhibit growth. But also, if we go back here and take this mutant strain, markerlessly deleted now, so no dodgy resistance cassettes, and you treat a mouse, and you take the CFUs from the lung. In the green here is that mutant treated with Q203, and you can see in a mouse sterilization in an order of a few weeks. And so now what we hypothesize from that is if we can get an inhibitor against this other enzyme and combine it with Q203, we potentially have an extremely effective regimen to take through into further lead optimization. So if you've seen our ugly mugs in a paper recently, this is the research that led to this. So this actually was published in PNAS, which is a leading academic journal. So now I'd like to move forward and talk about the second aspect of Bataclan that's really transformed our treatment, and that is this idea of activators as well as inhibitors for dealing with bacteria. So some work that we published a few years ago now, we showed this interesting effect of Bataclan on mycobacteria. That is, if you give mycobacteria Bataclan, again, coming back to oxygen, and in many ways it always does, Bataclan in this case actually increases oxygen consumption in whole cells and does not inhibit it. And the reason why this is important is the idea of persistence. When you become persistent, you're slow growing, you have very low metabolic activity. That means that cell wall antibiotics, drugs like that, that usually target growing cells aren't going to work anymore. So this is important, as you can see here, this fantastic experiment done by collaborators in virulent TB, is if you look at the oxygen consumption rate of TB as a function of oxygen concentration, you see TB in the wild type in the pink will very quickly stop respiring quite as fast in response to decreasing oxygen. It doesn't want to use up all of its oxygen. It's an obligate aerobe. It can't get anaerobic, otherwise game over. And what Bataclan does, increasing amounts in light blue and dark blue, is cause it to dysregulate its oxygen consumption, continues consuming oxygen till it gets down to almost as a lower concentration as in a hypoxic tumor microenvironment. So not only do they run out of oxygen, you've caused them to stop slow growing. They're no longer persistent. They've come out of persistence, reactivated. Whoops, I'm susceptible to frontline drugs again. So that's kind of the idea we went forward. Can we take this idea, make some activators, and see if we can target other respiratory proteins? Because I've been harping on about oxygen for a bit too much now, I'm going to switch tacks. We obviously have done some of these studies with oxygen. I'd like now to talk about a compound called NADH. So this is a lot further upstream in the pathway. This is right at the entry into the start of respiration. This is high energy electrons from which you derive the energy. Key compound produced by central carbon metabolism. I won't go into the details. So we discovered this compound, QQ8C. What we discovered is that if you take the proteins in TB that catabolize this to release its energy and transduce it, it activates that process, as you can see here in this graph on the right. What's really nice, again, is this length of time needed with this compound to sterilize the culture. Again, we're in the order of 2 to 3 weeks. Again, comparing to the isoniazid control where it just comes back. So this is quite a surprise, actually, because we just wanted to create synergistic combinations. And instead, what we actually found was activating straight up knocks out TB. Well, in this case, this is BCG, but we did confirm the results with TB. And again, this work was also published only last year. And we're now moving forward to try and see if we can create some interesting combinations for therapeutics from this kind of idea. So what I would like to sort of finish off on, because I'm aware that I'm sure you guys probably want to get to other pressing matters, is that we've taken these two sort of concepts and merged them together to look at even more effective antibiotics. And unfortunately, I can't really tell you exactly what those compounds are because of intellectual property reasons. The patents aren't really ready yet. But what I'd like to do is just show some of the kill data we have. Again, I told you our goal is to get to treatments that are in a 2-week time frame. And here you can see this compound X. In a free-growing culture of TB that is aerobic, it takes about 3 days to sterilize the culture, complete sterilization. And we can take this out for a lot longer, and we have not yet observed resistance compared to positive controls that would normally give resistance. What is really nice, though, is if you grow the TB up till it becomes hypoxic, emulating persistence, this compound X makes Bataclan look like a terrible drug, bearing in mind that Bataclan is actually a fantastic drug, so this is all relative. So you see Bataclan here, you get the hypoxia of the compound, you get a little bit decrease in the viability, which is enough. This other compound, compound Y, sort of the same thing. We think it's a mimic of Bataclan. This compound X, however, again, complete sterilization in a few weeks. So basically, all I'm going to say at the moment is watch this space. We're taking this through into sort of animal models, doing some medchem. Currently, the only problem we foresee so far is high clearance rates, but otherwise, once we get around the medchem on that, it should be very interesting. So what I've told you guys today is through this compound Bataclan, we learned that metabolism, respiration is a great target space. We don't need to restrict ourselves to thinking just about inhibitors. That's also turning enzymes on as well. And altogether, we've kind of learned a lot about how to make better drugs. So moving forward, we'd like to move forward from TB and into other organisms as well, starting to do work in Staphylococcus, Listeria, as well as considering moving into ESBL-producing E. coli. So that ends my presentation, and I just wanted to highlight that I'm only a small part of a large team. So I'd like to thank everyone in Professor Cook's lab, which is, we're now calling the Otago Bacterial Energetics and Antimicrobial Resistance Group. A bit of a mouthful, but the acronym was OBEAR, although I really wanted an acronym that was OBEAR, but oh well. With that, I've finished pretty well on time, and we'll hopefully have some time to take some questions.
I'm sure there are questions right there.
Catch. Oh, thank you. I'm just really interested in, I think I saw one of those articles that came out on the weekend talking about the Ganges having antibiotic levels which were similar to what you were trying to achieve in the human bloodstream if you were treating them. So there's obviously a huge antibiotic pressure on organisms to develop drug resistance. What happens if we actually remove that antibiotic pressure? What happens if we take antibiotics out of, say, agricultural production? Do we start getting bugs reverting to, do we know what happens? Will they revert to resistant organisms again?
There will be an energetic cost for the bacteria and maintaining these genes. Some of them are on plasmids that are going to have addiction systems so that the bacteria can't lose the plasmid. Some of them, they're also exquisitely regulated often so that they're only switched on when they're required. So I think it's speculation. I don't think we have a good example where I guess if you reduce antibiotic use, you'll see a decrease in the rates of resistance, but I think it's unlikely that it will go away.
I think a nice answer to that actually comes from the permafrost. Obviously, we don't really have great evidence at the moment. Well, I'm not familiar with it. Some may exist, but if you look at the permafrost example, far before the advent of antibiotics, there was already antibiotic resistance genes. So they were already there beforehand, and they're already going to be there in the future after we leave, if we leave. So I imagine it's always going to be a problem that's always sort of there. So I guess what I'm trying to say is we need to not sort of rest on our laurels like we did for the past 40 years and just sort of keep trying to iterate on what we've got at the moment.
But I think when you've got such heavy contamination of the environment, as you do, and it's been demonstrated in India and other parts of the developing world, when there's not necessarily good sanitation, where there's easy access to antibiotics, where there's a lot of antibiotic manufacture occurring, and a lot of that's being poured out into to rivers. We're still not entirely certain what role that plays in the cycle, I guess, of these genes coming back into the human population, but undoubtedly must be having some effect.
Sorry, if I can add a follow-up, because what's happening in the third world is sort of a demonstration of the failure of the market system, isn't it? The market is going to sell as many antibiotics as they can, and that just means that people make profits out of using them in agriculture, or people feel that they can feel better if they buy cheap antibiotics. And that makes it very difficult to develop new drugs, which are then going to be, you want to keep in reserve for the special infections. Actually, there's not much incentive to develop a new drug if it's not widely used.
That's, I think, a crux of the issue with new drug development is that if you develop a new drug, then Brendan and Jill and I and Angie, we want to keep it on the shelf. We don't want to use it. We want to save it where we really need it, and we want to use it for as short a time as possible, so there isn't a great economic incentive there. I think in many developing countries, there's not necessarily the regulatory framework that we have here, and that you can't, and that there is ready access to these. You don't not necessarily a pharmacy. You don't need to go to pharmacy to get antibiotics. You can get them from the corner shop. And I think in agriculture, there's perhaps even less regulation about what's available. Real concern.
I think it's also a big issue in countries where the antibiotics are not publicly funded, and so the patients has to shell out for 6 to 30 months of antibiotic treatment themselves. And in most cases, those people choose not to do that because they'd rather feed their families. So that's also the flip side of the issue, is that if the companies do make the money in countries without that kind of infrastructure, it's the people who have the disease, the infection, that suffer. There's actually a microphone in there, so hopefully it's turned on properly.
I turned it on.
Yeah.
So this one's for Kyle. So if you're moving on to target organisms like staphylococci and gram-negative organisms, how are you going to get around the problem that if you target the respiration, they'll just switch to anaerobic metabolism?
That's a great point. So that's something we're actively trying to look at the moment. Whilst we haven't published some of the data, there's definitely a lot of work in our laboratory that suggests that there's clinical relevance to some of the NADH consumption genes, but you can also take genes, for example, the complex 2, which is called the succinate dehydrogenase, in staphylococcus. There's lots of studies where they've treated them, deletion mutants of these in mice infections, and seen quite a big reduction in virulence. So whilst there's definitely fermentation strategies that bugs seem to be able to use in pure culture to escape this inhibition, we kind of hypothesize that in a site of an infection, OXPHOS may be more essential than a genome might give us the idea.
So another question for you, Kyle. So that was sort of my question too. But the related question is bacteria respire at different rates. So do you expect that sensitivities will differ if you transfer out of TB into strains that have different respiration rates? Or
that's actually a fascinating question. So I guess we don't really have a lot of fundamental understanding about if you for example plot a graph of, say, MIC, minimum inhibitory concentration, to the sort of nominal rate that the bacteria respire, we don't really have a good comparison there. I think for many bacteria, there's actually lots of literature linking respiration in general to virulence. So as far as a yes/no sort of answer, I can sort of say, if we knock it all out with a drug, that would be very effective. But as to sort of conceptually answer that question, it's a very interesting academic study, and it might just give me an idea in 5 years' time to write a grant.
and maybe a question. Oh, right.
Yeah, one of the questions was about the dormancy of TB normally, which I guess is respiratorily determined, and perhaps is it in granulomatous conditions even more hard to get to the last one if it's still sort of lying dormant, if it's resistant? Yeah, so I think this is the idea, I think that something that we didn't really touch on is this idea that in that persistent, hypoxic microenvironment in the granuloma, whilst they're not growing, they're still metabolically active, they're still respiring, they need to turn over, they still need to flux through this respiration process. So it's still active. So conceptually, yes, all the persisters should still need to respire. As for getting the last one in the granuloma, the real barrier may actually be getting the drug to penetrate into the barrier and into the granuloma. So I think the challenge there is actually going to be in actually getting the drug to the bacteria rather than making the drug effective in that case. But I think if we can achieve at least a great enough reduction in bacterial load, hopefully the body will be able to take care of the last bits itself. Just to comment, the whole thing is a bit like gun control in America to me, that it's a humanity-induced problem which there's too much in terms of secondary gains to actually deal with the problem directly. So if agriculture is dependent on conditioning due to antimicrobials in massive scales, we seem to be fighting ourselves eternally without ever going to get on top of it.
Yeah, that's definitely a valid point, and that at a very political level, that sort of maybe speaks to perhaps a more government level regulation of how we're using our antibiotics. Although perhaps at a sort of more personal patient level, I would argue that it's not the fault of the person who got TB, that there's antimicrobial resistance. It's the fault of someone else. So that becomes a philosophical question. Who can we say we should choose to save someone or choose to not because of, say, one person ruining it for the rest of us?
I mean, I think with the issue of how much we can get rid of, I mean, we need antibiotics. We need to use them well. We need to try and reduce the selective pressure, but we still want to be able to use antibiotics when we want to be able to use them, whether that is the New Zealand Veterinary Association clearly feels that they can, that antibiotics are not required for other than treatment and prevention of disease. They're not required for growth promotion, and they're looking to get rid of that. From a medical perspective, I think we need to look at using the narrow spectrum antibiotic we can, using it for a shorter duration as possible, and using it only when we need to use it to try and reduce that selective pressure. There's still going to be a selective pressure, but hopefully we can preserve what we have for a little bit longer, and allow development of new drugs, which is clearly what we need. And we need things like these new targets that are outside the sphere of our current range of targets. And it'd be great to see the New Zealand Medical Association or other professional groups take a lead from the New Zealand Veterinary Association and come up with some targets for reducing antibiotic usage in certain circumstances and improving antimicrobial stewardship.
I think the trail of thought that antibiotic courses need to be taken into account regardless of symptoms that can start early. Recently, we've heard a lot of talk about actually that thought is starting to change.
Yeah, I mean, I think that's dogma and it's wrong. So I think, yes, we've always said take your antibiotics till the end of the course because we're worried that the bug we're treating might develop resistance during treatment. The reality is that most antibiotic resistance isn't due to mutation. There's a few examples, quinolones where it is, rifampicin, but in the majority of cases it's acquisition of a gene. All we're doing by treating for longer is providing more selective pressure. We shouldn't be worried about if we're treating a throat infection, the bug in the throat becoming resistant. We need to be worried about the effect of that antibiotic on the gut microflora and the selective pressure that it's providing there. So I would argue that we should be looking to treat for as shorter time as possible. And there are not a lot of good studies about duration. We often don't know what the appropriate duration is. There are clearly examples like endocarditis and bone and joint infections where we do need to go for a long time. We know something about duration, but there's been a couple of studies that have come out recently, one in the New England Journal from the end of last year that showed if you've got an abdominal sepsis, if you've got good control, surgical control, then 4 days is fine. If you've got, there's a recent study that came out that said if you've got ventilator-associated pneumonia but you're relatively stable, then 3 days of antibiotics is probably all right. So do we really then need to treat someone with bronchitis in the community for 10 days?
Although one comment I'd add is I'm familiar with that research, and I believe the study was treating patients until they felt better. So I'd argue that we need something a bit more standardized than when a certain patient feels like they're good, because that's just really not scientific at all, and it could lead to undertaking the course far more than they should. So we kind of need a better. There's room for improvement, but I don't think the patient deciding when they feel better is potentially the best way to decide the course length.
Well, it seems to me, and I'm just thinking, there's been a lot of funny, chesty, fluey things around Dunedin, and I'm conscious my wife came home with a prescription yesterday, which is for about 3 weeks. Surely there needs to be a way of monitoring her state of health so that after 5 days, 3 days, she can get some sort of quick test over to you guys to say, enough, stop taking it.
Yeah, there is actually a great scientist in the back of the room who's starting to develop some of these technologies, at first for TB, and that is the use of whole genome sequencing, in this case, as a diagnostic tool, Myanmar for TB. As these technologies become more available, we'd actually like to see that more routinely used as a broad diagnostic test. So that's still a long ways off, but that would be my hope, is that we can make simple whole genome sequencing available, because obviously the benefit is we detect all kinds of resistance as well that's happening.
Yeah, I mean, I guess it depends on what the infection is. I mean, if it's a urinary tract infection, then 1 dose of the antibiotic is probably sufficient, even if, and most people are going to get better anyway, even if you give them non-steroidals to alleviate symptoms. There's not that much. People don't get that much better that much quickly on antibiotics than they do if they take non-steroidal anti-inflammatory drugs. So, I mean, I guess a lot of our use of antibiotics has to be questioned. I mean, at a broader level, you could say that maybe if there was better access to primary care, if it was cheaper, then maybe you could be reviewed and say, okay, well, you're much better, we can stop after 3 days or 5 days, whereas there's quite a financial disincentive to go back and to see the GP in our current setting, given that it's essentially not a government-funded system.
There are huge political manifestations in all of this, and we're all conscious of the use of antibiotics in the manufacture of food, notably Southeast Asia. And I'm mindful of Chernobyl, where that big bloom went over Europe, and the shit hit the fan, and the whole world pretty much has got that contained now. You don't get away with knocking at Chernobyl over the world. Why can't we be doing that with antibiotics and food manufacturing? It's a political thing. So you guys need to get onto the politicians and get our government to talk to other governments, and there should be a worldwide awareness of this. So it's a political thing. It's not. And I'm also thinking, Madame Curie gave her discovery over to the world. She would not patent it. Similarly with Röntgen, with his discovery of X-rays. Shouldn't you guys be sharing and not patenting?
That's actually a great point. There have actually been several drugs that have actually been developed and seem to be effective by some. It was actually, I can't remember the name of the guy. He's invited down to QMB, presented to research, and yeah, there's some great drugs that have come through. They've not been patented, and no company's taken them up to mass produce them because the IP was already out there. So I guess that the thing is, it comes back to this idea of the financial incentive for the company. If we don't have any kind of financial incentive for the only people who can mass produce and deliver a drug, then simply great drugs go under the table. So, it sounds kind of heartless to say, I'm not going to tell you about this great drug because I need to patent it first. But if I don't patent it, then I might as well go home and sit my ass and do nothing.
Okay, so thanks very much for an excellent seminar, James and Kyle, and it certainly generated some really good discussion here. And yeah, I wish we could keep going, but it's just gone 2 o'clock, so we better draw it to a close. So thanks again.
John Blanchard, that was his name.
Yeah, thank you.